Hello everybody, how's everybody doing? I hope you're doing fine, doing better than me. Okay, and today we have an exciting day. Exciting day in physics. In physics, yeah, not in mathematical physics. There it's not going to be very exciting. Today we're going to do a little bit of semantics. People say, Bill, I didn't come here to learn grammar. I came here to learn about physics, see if there's anything new about physics, right? Yeah, but physics starts at grammar, semantics. We need to understand the meaning of words. There are some words where apparently the mathematicians are having a lot of trouble with. And so do a majority of people because they simply introduce the notions of ordinary speech. That's where the problem starts. They introduce these notions of ordinary speech into physics. They use them like they use them every day, and they cannot be used like every day in physics. Okay? So what is semantics? Let's find out. Semantics, the branch of linguistics and logic concerned with meaning. We're going to talk about meaning. What is the meaning of words? How should they be used? Especially for the purposes of physics. Keep that in mind. A lot of people, again, are thinking in terms of ordinary speech, and you cannot bring some of those terms directly without scrutiny. You need to look at them very carefully. What do they mean for the purposes of physics? One key word is always, words such as motion. In ordinary speech, that's a noun. So is the word orbit. Well, in physics, those are verbs. Physics, you cannot say orbit and think that you're talking about a physical object. Only physical objects can be nouns in physics. And there are other words that I'm going to get to in a second here. It says the two main areas are logical semantics, concerned with matters such as sense and reference, and presupposition and implication, and lexical semantics, concerned with the analysis of word meanings and relations between them. Okay, and Wikipedia says something similar. Semantics is the linguistic and philosophical study of meaning in language. Okay? It is often used in ordinary language for denoting a problem of understanding. That's good. That's a good statement there for physics, for science. That comes down to word selection or connotation. Yeah, that last statement is very much applicable to physics. So what word am I concerned about? What words am I concerned about? I'm concerned about these two words here. Prepositions in and through. Can we be in space? Can we travel through space? The answer is no. You can't use these terms in the context of space. That's what I'm going to argue. That's the starting point. And then I'm going to get to Al-Khalili, who actually uses these words in like being in space, going through a dimension, and so on and so forth. That's why I had to bring this subject up. Okay, yeah, you can't use these words in and through in the context of space. Okay, so let's find out why. Okay, here's the in preposition. Okay. And it says used to indicate inclusion within space. Within space, maybe in ordinary speech. Not in science, not in physics. A place. No, we can't be in a place, not in physics. Okay? Place is a concept. We can't be inside concepts or in concepts. Or limits. Now there we're getting closer. Yeah, you have to have limits. Then you can talk about being in a container of sorts or inside a boundary. That's the context of physics. Okay, and you need to understand that every time I hear the word in the context of space or other concepts such as places and so on, that's not what we mean in physics. But even under some circumstances, like you could say, I'm in China. What do you mean by that? Well, you mean that you're within the borders of China, and then it's okay because you're referencing yourself to that edge, to those borders. Then it's okay if that's what you mean, if that's the context. Okay, so let's keep that in mind. Walking in the park. Yeah, if the park is this area that's got a border, and we call that the park, then yeah, you're inside the borders of the park. Then in is correct, okay? That's the context. That's the usage for physics. And it says used to indicate inclusion within something abstract or immaterial, like in politics or in autumn or in the autumn or whatever. Not in science, not in physics. Okay, so this version of in, it does not apply to physics. I hope I'm still on. Yeah, I think I am. Just checking to make sure I'm still alive. Sometimes they cut me off here at YouTube and I talk in the air. Okay, here's an example of in. You got a couple boys, they're in a barrel. That's in. They're inside the borders of the barrel, okay? Can you be in space like this fellow here, okay? What is it? Leonardo da Vinci's man there, okay? Well, only if space has borders. Then you can say that you're in space, okay? Then only under that context can you say if space has borders. That's what you're suggesting. You're suggesting space is a physical object. And a lot of people do have that notion of what space is. They think that space is a physical object, okay? They treat it as a physical object, okay? Can you be surrounded by energy? Can you be in energy? Well, hopefully not, because, you know, you can't be in a concept. And that's the issue with space as well. You can't be in energy. You can't be in mass. You can't be in time. We're going to deal with that a little later. You can't be in space. Okay, you can't use that preposition in any of these contexts for the purposes of physics. So again, what we do in ordinary speech is unrelated to what we do in physics. Physics is done with physical objects, okay? And you need a physical object. You can't say that you're inside a concept, which is essentially what relativists say. They say you're inside space-time. This Big Bang that still is exploding. The Big Bang was 14 billion years ago, but we're still expanding. That's the universe. No, you can't be in space. You can't be in Big Bang. You can't be in space-time, 4-dimensional or otherwise 26-dimensional, whatever they come up with. You can't be in a concept. You can't be in love. Not in physics. Maybe in ordinary speech, poetry, yeah, that's fine. Not in physics. So keep the prepositions proper, you know, use them properly. And here the issue is that people are applying them to concepts like they do in ordinary speech, and they just bring them into physics, straightforward, without scrutinizing. Okay, so here we have, again, Leo's man. As long as he's in space, he's wrong. Because what you're suggesting essentially is that there is a border to space. What you got to identify if space is an object is that white stuff. I need to know what that white stuff is if space has border and you're in or within space. Okay, so that's the issue. The issue is that you can't say that you're in space because of that. Because when you use the preposition in that sense, you're saying that space has borders, space is a physical object, and you only have a single duty, and that's to identify that white spot, space, the white stuff there on the picture. Okay? So, not in space. You're never in space. Okay? Here's another preposition. That's the preposition through. Talk about going through space, through dimensions. Is that possible? What does it mean? The preposition is in at one end, side or surface, and out the other. Well, hopefully if it's got an end, a side, or a surface, it's a physical object. So you can't go through nothing, and you can't go through a concept. Hopefully time is a concept, and hopefully dimension is a concept. A number line, that's what they use in mathematical physics. So, you know, you can't go through that which is not an object, okay? We drove through Denver without stopping. Sun came through the window, okay? Remember, through Denver, only if you treat it as a physical object like a city and you say, well, we went through this piece of land. That's okay. Okay, but you can't go through a concept like if you treat Denver as an abstract concept like a city. No, if you treat it only as a land, a piece of land, then you went through Denver. Okay, you want to call that piece of land Denver to differentiate it from something else, that's fine. You say, I went through this piece of land. That's fine. That's the context for physics. Not ordinary speech, but physics, okay? Went through the window. Hopefully a window has surface, side, end. Hopefully it's a physical object. Yeah, you can go through things. You cannot go through that which is not a thing. You can't go through nothing. One of the things you can go through is this thing we call a tunnel, okay? And that's very important in mathematical physics because they're going to use this tunneling just about everywhere. They use it in quantum mechanics. They use it in the wormhole scenario in general relativity. So the tunnel is going to be very important. They're going to tunnel through everything. They're going to tunnel through a dimension, etc. What is a tunnel? Well, it's a noun, okay? An underground passage. Well, underground, that means it's got a border. It's got, a tunnel is some kind of hole. There you see it at the bottom left. Some kind of hole, walls, or even if it's just a dirt, it doesn't matter. But there's something, there's a surface. You're going through a surface, okay? Obstruction as in a city, mountain, river, harbor. Yeah, any of those is fine. You're going through a physical object. You can go through molasses. You can go through air. You can go through water. You can't go through a concept, okay? It's very hard sometimes for religious folk to understand that you can't go through a concept, an abstract concept. You can't use the word like that in physics, okay? You can go through a cloud. Cloud is a physical object, okay? But you can't go through nothing. You can't go through space specifically. You can't say in space or through space, okay? What is it? You can go through a mine, okay? Because what a mine is an underground, it's got ground, earth around it, Burrow of an animal, same thing. There's a burrow down at the bottom right, okay? So you can go through any of these because it's enclosed. It's got walls. You're going through these walls that are all around you, okay? You got a ceiling, you got a floor, you got a wall maybe. You got to go, in order to go through, you got to have some physical object. You don't go through concepts. You don't go through abstractions. Here's a tunnel, okay? And you can see it's got walls. You got the cars going back and forth through this tunnel. And yeah, hopefully when you go through a tunnel, you're talking about going through something and not going through nothing, okay? That's a tunnel. It's got walls, okay? Okay, I hope I made my point for these. So, well, here's one more. Okay, here's a rocket, and if it's going through space, well, then space had better have walls, and you got to identify that white stuff there on the edges. Okay, so if the rocket accelerates and you say it's going through space, you're treating space as a physical object. You're saying space has borders, has surface, it's not infinite, it's finite, and all you have to do is identify, that white stuff that surrounds space and gives shape to space. So that's the tunnel of space, okay, if you're going to go through space, okay? Makes sense? So you got to be careful with the semantics here. Yeah, it is important. You might say, Bill, that's grammar. I don't like semantics. I didn't come here to learn English. We're not talking English here. We're talking about semantics as related to physics, as related to science. You can't use these terms unscientifically by applying it to the same context as you do in ordinary speech. Okay, that's the point. Okay, so what do we use in science and physics? We use the preposition to, okay? And so what is the preposition to? Used for expressing motion or direction towards a point. Person, place, or thing approached or reached, as opposed to from. They came to the house. Okay, for example, an example. No, you go to the moon. You don't go through space, or you're not in space. You're going to the moon. You go from one object to another object in physics. Okay, and hopefully, if you go through some other surface that contours, some kind of tunnel. Then you're going through. Or some kind of medium, could be air, could be water, molasses, again, it could be any of those, okay? So yeah, you go to the moon, like in the cartoon down at the bottom, picture 1902. You leave Earth and you go to the moon. One object to another object. That's the way it works, okay? And no, we do not use it for point, whatever point is, unless they're talking about location, towards a location. But you don't go towards a location. You really go to whatever's at that location. You go to the stop sign or towards the stop sign, okay? You can go to a person. You can't go to a place. That's, again, a location. Thing, yeah, you can approach a thing. Okay, person or thing, which is the same thing. They're all things. You can go to things. You cannot go towards concepts. I cannot move towards a concept. I can't say I'm going to space because there is no physical object called space, so I can't go there. You can only go to, I can go to Mars. Mars is a physical object. I can go to the moon, if I'm going out there. Or I can go to a stop sign or whatever, to the end, to the light at the end of the street. Then I've got something. But you can't go to love. How do you go to love? I mean, what does that mean? So here it is, summary. You can't run towards love. You can't run towards a concept. And you can't run from or away from a a concept, like in this case, tyranny, okay? No, in science, we run from objects, like in this case, a wall to a cylinder or to a pipe. Okay, you have to run from object to object. Okay, hopefully that all makes sense to some of you at least. Okay, so what's the problem with Al-Khalili? How does he use these terms? Well, he's going to take us through a wormhole, whatever that is. We're going to find out. We're going to try to find out what it is. He's going to take us through a dimension. He's going to take us through time to the future. And I don't know what the future is. I hope I don't land in the future, whatever it is. I hope it's solid so that I, land with my feet there. Or maybe I hope if I fall from far above, I hope it's liquid. So whatever future is, I'd like to make sure it's a physical object of some kind, right? I don't want to land on a concept. And then the other issue is, whether it makes any sense to say that you're going to travel through a dimension, through time, through a concept. And again, I'm saying that you can't. But that's what Al-Khalili does. And he starts out like where we left off the other day. Okay, here it is. He said the following. He says he's going to take us to the future, okay? He says another option with a black hole is a bridge. And that's the Einstein-Rosen bridge, okay, which is that famous wormhole that is on people's lips today because everybody wants to go to the future, the past. Everybody wants to get out of the present. Coronavirus, It's a tunnel to somewhere else. Well, somewhere is one thing, and the other one is when. And that's different. Either within our own universe, whatever that means, or if parallel universes exist into a parallel universe. And again, this parallel universe, you have to distinguish what is different from that universe and ours. If we share the same space, if there's only a single black stuff out there for all the matter that's rolling around, floating around, then there is no other universe. There is only one universe because universe is space and matter. Now, if there's some kind of isolation, physical isolation of sorts, between that universe and ours, like in the case of the rope model, there could be, if none of the ropes from that universe, which all these atoms are interconnected over there, and all our atoms are interconnected over here, but none of our atoms are connected to any of the atoms of that other universe, then you can talk about two universes. For example, the example I always give is the Andromeda Galaxy. It's got all these atoms there that make it up, right? But we can see the Andromeda Galaxy. Why? Because all the atoms in the Andromeda Galaxy are connected to your eye through the electromagnetic ropes. So you got gazillions of ropes, all of them, and they converge upon the one atom in your eye and a bunch of atoms in your eye. So the Andromeda Galaxy belongs to our universe because it's physically connected through electromagnetic ropes to our universe. But there could be another universe we could call that's got all this matter and none of that matter is connected through electromagnetic ropes to any of the atoms in our universe, then that would be an isolated universe which we would not be able to see and from which we cannot feel gravity. Okay? Only under those conditions. But in the case of mathematical physics with all particles, which is a particle universe, I can't see how they're going to isolate themselves from that. Whatever they put, even if they put a wall, that wall and the other universe belong to our universe. It's all the same universe. So they can't talk about parallel universes until they define the word universe. Otherwise, we have no idea what they're talking about. What do you mean by universe? And that's when they start saying, well, it's contextual. Here we use it here this way, and here we use it in a different way. Okay? He says, nowadays, physicists are very convinced by the evidence. Yeah, convinced by evidence. That's what the purpose of evidence is, to convince you that black holes exist. No, exist. If black holes exist, they exist by definition. They have to be objects and they have to have location, meaning they have to have distance with respect to us. Otherwise, they don't exist. And of course, a singularity, a zero-dimensional singularity, very unlikely that it exists because it has no location, it has no nothing. It's inexistent by definition. It has to be an object to exist, and a black hole is not an object. It doesn't have any shape, which is the definition of an object. Okay, so convinced by the evidence that black hole exists, but what is inside a black hole? Should be all mass and no matter. Even though mass is the quantity of matter, a black hole has no matter, but it has mass. So you figure it out. It's a circular argument that the mathematicians created for themselves. Whether there is a tunnel or a route to somewhere else is complete speculation. No, it's no speculation. Absolutely nonsense. That's what it is, not speculation. There can't be a tunnel, a one-dimensional tunnel, because the black hole is a zero-dimensional nothing. All matter has been crushed out of existence, as we showed a couple weeks ago. Okay, it's allowed by the mathematics, perhaps, but not by rational science. Okay, but we don't know how true it is. No, it's not true at all. If Mother Nature holds the truth, she frowns upon black holes. For sure. She doesn't like them. She doesn't like to deal with nothing. She can't handle the nothingness of black holes. Okay. What's wonderful about this idea of a tunnel is that it could allow for us to build a time machine. Yeah, that's why they created this nonsense, because people wanted to say, well, are we stuck here on Earth? Rational science says, yes, we're going to die here on Earth. That's it. We're done. These people wanted to give you hope, false hope. You know, you're on Titanic. Oh, it's okay. Don't worry. Nothing's going to happen. You know, and it's more or less like that. You know, you fall from an airplane. Yeah, it's okay. You're okay so far. And when you get down there, I don't think nothing's going to happen to you. I don't know. Yeah, so they give you false hope. They say there is a future. And the future is in colonizing the planets, the stars, the galaxy. No such monster. No, life cannot travel interstellarly. And that's a long story. Okay, so he had to give you hope. And so you say, well, how do I travel to the next star, to the nearest star? And they say, okay, we can't do it at the speed of light because Einstein said that's forbidden, right? And he's the boss. And so the way we do it is we have to take shortcuts. We go through the time dimension. We go through somewhere else. We beat the speed of light because we take a shortcut and light doesn't know about it. Light is so stupid, it goes through, through regular, ordinary highway, and we take that shortcut, you know. And what's nice about Al-Khalili is he tells us right off the bat that his world is a world of Alice in Wonderland. And he says it just, you know, like candidly. Alice in Wonder is a wonderful example of Einstein-Rosen bridge. Yeah, no kidding. So we're talking about not even science fiction, and we're talking about fantasy. Okay? Alice chases the white rabbit down an Einstein-Rosen bridge. There you have it. I mean, I didn't say it. These are his words. To a parallel universe. Is that what science has become? Alice in Wonderland? These guys seem to be reading too many comic books or fairy tales or they've been watching too many Hollywood cartoons or movies or who knows what. Maybe that's where they got their degrees, Hollywood University. Alice is looking glass. She's going through a wormhole into a parallel reality. Oh yeah. A lot of people have parallel realities, you know, when they drink too much or whatever. Okay. So he's going to take us through this wormhole, good old Al-Khalili. He's just going to fall in there. I don't know when he's going to find one, but he says he's going to go through this one-dimensional wormhole. And it doesn't look like one-dimensional to me because he's three-dimensional. If he's three-dimensional, this wormhole at least has to be, I would think, three-dimensional. Okay? I can't imagine him going through a one-dimensional because anything because he'd be, squeezed into a linear spaghetti, So I don't know how he can say that he's going to go through a one-dimensional anything. But that's what he's going to take us on a trip there. Okay, so get ready. I hope you packed your bags. Okay, are you ready? We're going to take a trip with Al-Khalili down Alice in Wonderland wormholes. Okay, and this is what a wormhole looks like from the inside. Okay, so it looks kind of like this. So if you're scared of mysterious things, you may not want to go. Okay, so this is what it looks like. Okay, so just so that you can see what you're going to experience. Okay, these are what people illustrate when they talk about wormholes. Okay, and the other day I showed you that this is what they do. They make you go through the time dimension. That's what a wormhole is. Essentially, the wormhole is a time dimension. What they do, they have these coordinates coming up here in a second. Give me a second there. There we go. So you can see its height and width, and they turn it into time and space. Space supposedly the three dimensions, and they're not even going to go through the three-dimensional space. They're just going to assume that time is fat enough that you can fit your three dimensions through it, and they just go through the dimension of time, which is what, a one-dimensional dimension? Okay, and that's the Lorentz factor there. The faster you travel, okay, closer to the speed of light, well, the more time dilates for the observer. Okay, he sees you going very, very slowly, and so he measures time differently than you do. That's what they want to tell you, and that leads to what I covered the other day, the twin paradox, and just a comment on the twin paradox that you should note here. Let me put good old Al-Khalili's Einstein twins there. Okay, yeah, we have the two Einstein twins. Al Einstein stays behind on Earth, and Frankenstein, he goes to, I don't know, to Mars at the speed of light. He comes back 20 years later on Earth, 20 years. But he went so fast that for him only a few minutes went by. Okay, so he comes back, as far as he's concerned, he just spent 1 or 2 minutes out into space, and he meets his brother Al Einstein, who has aged 20, 30, 40, 50 years here on Earth. They have all these calculations, right? And someone asked Al-Khalili the right question the other day, a woman. And she says, because it's the issue that I raised a long time ago as well, the Earth is what we use for the word year, to define the word year. The year is one orbit of the Earth around the sun. That's the definition of year, even to this day. They haven't changed that. We don't count years by counting seconds on an atomic clock. We say, how many times did the Earth go around the sun? Well, it went 3 times. Well, you're 3 years older. Period. We're done. And so now here's Frankenstein. He goes all the way to Mars. Speed of light, or close to the speed of light, doesn't matter. Comes back 50 years later. And so this woman asked Al-Khalili, says, well, hold it. How many years went by? I mean, if the orbit of the Earth is what we use to define the word year, and the guy on Earth went 10 times around the sun, or 20 or 30, 30 years went by. It's straightforward. What did Al-Khalili answer? He said, well, from the traveler's point of view, right? From the traveler's point of view, he measures time differently. So for him, the Earth went around the sun much faster, okay, because he measures time in a different way. Well, Al-Khalili is either not very intelligent, or he doesn't understand physics. I don't know what the problem with him is. This is straightforward. So let me make it clear to Mr. Jimmy here, okay? See if he understands. Frankenstein goes out to Mars. He comes back when the guy on Earth suffered 50 years. In other words, the Earth went around the sun 50 times for the guy on Earth. When the two guys meet again, we should have, I don't care how many times the guy measured while he was in Pluto or in Mars or wherever, when he comes back to Earth, we know for a fact that the Earth went around the sun 50 times. So I don't care what his clock measured. I don't care what the mathematical calculations say. I don't care how much he aged personally, physically, physiologically. When he comes back, the Earth went around the sun 50 times, whether he likes it or not. Okay, so only 50 years went by because that's the number of revolutions the Earth went around the sun when he comes back and meets his brother. So it doesn't matter how many times he counted from far away, how many revolutions he counted. When he comes back, he arrives when the calendar on the wall says 50 more years. So if he started his trip at the year 2000, he comes back at the year 2050 according to the calendar on the wall. That's how many times the Earth went around the sun. That's how much we counted. We don't measure these things, we count them. And when he comes back, he's going to find himself in the year 2050. So he might say, well, for me, only 1 year went by. So for him, according to his clock, it's only 2001. But according to reality, it's 2050. So I don't know what mental problem Jim Al-Khalili has in understanding such a simple issue. This is straightforward, okay? And again, it's the difference between physics and mathematical physics, the nonsense of mathematical physics. Okay, so where's Al-Khalili going to take us? Well, he's going to take us to Andromeda. Andromeda Galaxy is what, 2.2 million light years away. That means traveling at the speed of light, you arrive in one way, 2.2 million years. That's how long it's going to take you to reach there. If you do a round trip, well, it's going to take you 4.4, somewhere around there. Some would say it's 2.5. Doesn't matter. After 2 million, I stopped counting it. Okay, so this is what he says. Instead of going the long way, the way we see Andromeda there, straight line to Andromeda, why don't we take this wormhole and just cut corners, okay? So this is what he's suggesting that we do, that we just cut across and go through this so-called wormhole. And so this is exciting. I mean, I can go through some kind of burrow, some kind of hole in the ground and reach Andromeda faster than going straight. I mean, we stare at Andromeda. You can stare at it every night. If you have a telescope, you can see Andromeda over there. And you say, okay, Andromeda, if I have a straight line of direction from Andromeda to me, that's the way light travels. That's straightforward. I can't go faster than light, okay? So if I traveled at the speed of light, 300,000 kilometers per second, in the direction of Andromeda, straight line, I would arrive in, 2.2 million years. It's straightforward. I mean, even the mathematics is straightforward. There shouldn't be any question. What do they do in mathematical physics? What does Al-Khalili do? He says, well, you got to take a wormhole. And so what is this wormhole? How can it cut corners? Well, here you have a picture of what a wormhole looks like. You go underneath, I guess, the canvas, the fishnet of spacetime. Spacetime is flat, but you take the curved road. Well, even in this case, you would think that if I take the curved road, I would take longer than going straight ahead, right? I mean, look at that. If you go along the sheet in a straight line, well, then since it's a plane, it's a flat surface, you should arrive faster than going through the wormhole, which takes you to some kind of curve. And what they're saying is that curve is shorter than the straight line. That's what they're going to tell you. That's what they're going to try to convince you, because they're going to go through some unseen dimension, something you can't even feel or sense or imagine. You can't even imagine this thing. They're saying it's some kind of shortcut, which is the long cut. Okay? And the way they do that, remember, space-time is a flexible entity, okay? So it looks more or less like this. It's malleable, okay? So, but even in this case, like if I go straight through the surface of space-time, man, I would fall into all these potholes. If anything, it slows me down. I mean, I would rather have space-time be a flat surface that's not malleable. I would get there straight along a plane, period. We're done. But if this is a malleable surface, then, you know, we're talking about, you know, moving up and down and falling into potholes. It would look something like this, like, you know, here you have a stairway to heaven, okay? You know, it's a curve, and a curve takes longer than a straight line. I mean, we learned this in Geometry 101. It's a no-brainer. And these people are struggling with this stuff. They're saying, no, we go through this malleable sheet through the wormhole, which is a curve, not a straight line, and that curve is shorter than a straight line. Why? Because it goes through another dimension. That's what they're trying to tell you. Let's see if we can visualize this, or at least illustrate it somehow. Okay? We're going to bend space-time. Okay? If I can get this thing up here. Okay? Okay, this is what we're going to do. We have flat space-time. We're going to bend it around, okay? Listen to what we're going to do here. We're going to curve space-time fishnet, right? Here's the photon trying to run the straight, you know, the long path, and we're smarter. We take the short cut, which is the wormhole, okay? And so while the stupid photon goes all around, we can go from one galaxy to the next by cutting corners. Now, how's that for speed? So we can even beat the speed of light without traveling at the speed of light. That's what these people are trying to tell you. They want to give you hope that there is a future, that we can go to the stars and to the galaxies. Sounds like a sales pitch to me, like they're trying to sell you something, mathematical physics, you know. So this is it. This is what they're trying to tell you. It says you travel through the shortcut and beat the photon. That's in a nutshell what these people are trying to tell you. Now, of course, you got to bend space there. Actually, it's you're doing something else. And I want you to keep this in mind. And again, some people equate the universe with space, space with the universe. No, not in physics. Slap, slap, okay? Let's see if we can wake you up. Universe equal space and matter. That's what the word universe means. Space and matter. Stars, galaxies, asteroids, planets, atoms, the whole works. That we'll call all that matter. The two shebangs, this so-called space thingy and matter, that's what we call universe. So universe is a concept. There is no physical object called universe. So you cannot say whether the universe is finite or infinite, because those words finite and infinite only apply to objects. Universe is not an object. We're done. You can talk about whether a tree is finite or infinite. You can talk about whether a house is finite or infinite, or rock, and so on. Okay, and hopefully none of them are infinite, because otherwise you wouldn't know it's a rock, right? But space has no borders, so space is not infinite either, because there are no infinite concepts, except in mathematics. They talk about infinities and nonsense. In physics, there is no physical object which is infinite by definition, because all objects are finite. What is an object? That which has shape, and hopefully all shapes are finite. We're done, okay? That's how it ends there, okay? But what these people are saying is they're going to curve the universe, not space, okay? This is what they're going to do, okay? Keep in mind, what they're going to do is they're going to bend the universe, okay? This is what they're going to do. They're going to bend the universe. If you start out with a universe that looks like this, with a Milky Way straight ahead to the Andromeda Galaxy, they're going to curve the universe around in Andromeda. They're going to put Andromeda on top of your head, and now they're going to go through all these stars and galaxies and whatever, through this dimension to get to the Andromeda Galaxy. This is what they're trying to tell you, okay? Yeah, like someone says, the tortoise and the hare. Yeah, I guess the tortoise took a shortcut to beat the hare. But see, what they're bending is the universe. If the Milky Way is straight ahead, we can see the Andromeda Galaxy straight ahead with a telescope every night. Okay, you see it up there in the sky. And light from that galaxy comes directly to your eye. That's a straight line distance. These people are curving, putting Andromeda on top of you and saying they can cut corners through who knows what space, what medium, and they're saying they're going to go through the time tunnel. Well, is a time a physical tunnel? Is it a thing? Are you going through it? See, this is where they use the word through, and you can't go through time because time is a concept. So they're treating time as a tunnel. And so the only question there is, what gives shape to this tunnel? Tell me what the pipe looks like, the walls of this thingy that I'm going through. What does that look like? And is it three-dimensional? If it's three-dimensional, we're not talking about the one-dimensional time anymore. Now we require 3 dimensions to go through time. Okay, am I making sense here or not? These people are saying you can go through the time tunnel. Okay, that's what they're saying. So they're bringing nonsense into physics, into science, and they're saying you can go through this one-dimensional whatever. And I don't know how you can squeeze in there, but they're saying it's a tunnel. Oh, okay, if it's a tunnel, I'm okay. That means it's got walls. It looks like a tube, I guess. In fact, the wormhole is illustrated like a tube. Means it's 3-dimensional because it's got length, width, and height. Okay, remember? All burrows, rabbit burrow is length, width, and height, and so on. It's the hole inside the ground. So we say the burrow, we're talking about the hole, but really the hole is a tunnel. What is a tunnel? Well, it's got walls. That's the point. It's got depth. Okay, it's got the height, you could say, or whatever you want to call that extra dimension there. So that's what they're saying that time is, some kind of tunnel. And it's cutting through what? We don't know. It's a one-dimensional what? And see, they don't clarify these things because then that's when they revert back to mathematics. Okay. So yeah, if you want to, according to these people, if you want to send something to your friend over there in the Andromeda Galaxy, all you have to do is just put it into a black hole here, and it comes out of a white hole over there, okay? And your friend will receive it on the other end. Meanwhile, what we have is that light, which is, you know, a dumb photon, doesn't know any better. Light's going to take the long path somehow. It's going to go around. Even though, you know, we see Andromeda in the night sky there right in front of us, straight line, they say the path of light, when you talk about 4-dimensional, is somehow curved, whereas the dimension of time, that's 1-dimensional, we go straight. So if you put the box here, and that's your time tunnel there, the wormhole, then your friend over there in the Andromeda Galaxy will receive the package instantaneously at the speed of thought, okay? Why? Because that's what a wormhole is. There is no time in a wormhole. I mean, you can put anything you want there. You're not even talking fantasy because you cannot even imagine this stuff. This is all surrealistic. You cannot even conceptualize what they're saying. And they can't either. And they say, we can't imagine it. Of course you can't, because you're introducing garbage math into physics. That's why you can't imagine it. And where does this all come from? Particles. Particles, particles. We've been dealing 2,000 plus 3,000 years maybe with particles. We got to get rid of the particle hypothesis. Anyone today using particles as a mediator has a mental problem. Rational science, we treat them as mental patients. Okay? So if you talk about the ether, a bunch of particles, you talk about waves, the waving of particles. If you talk about any of those, you talk about quantum mechanics, you talk about the the electric universe. They use the quantum atom, Bohr, Rutherford, planetary atom. All these people have mental problems because they have never figured out that you can't continue simulating physics with particles, the invisible stuff. Light, gravity, magnetism. You can't simulate them with particles. Hopefully, if every atom in your body is attracted to every atom of the earth, that means every atom of your body is connected, physically connected to every atom on earth. Why can't you see it? Why can't you touch it? Why don't they get tangled? Because Mother Nature in her wise wisdom made them invisible, intangible. For otherwise, we would be tangled up in knots. So first, she was smarter than the person who asked that question and says, look, if I would have made them tangible and visible, That's all we would see, and we would be tangled in knots. That's the main reason. But then aside from that, you have to define what touch is. And that's where people get a little nervous because they can't define the word touch. And yeah, that's in my book. I'm not going to go over that here. Okay, so that's food for thought for today. Semantics, very important. In, through. You can't go in space. You can't be in space. You can't travel in space either. And you can't go through space. You travel to objects, from objects to objects. Okay? You travel from the gas station to the train station or whatever. It's got to be from one object to another.